get started. Good morning. We're going to be talking about principles of flight, engine and operative. We're transitioning now to the seminal multi-engine aircraft. So why do you want to fly a multi-engine airplane?
Two engines.
Okay, two engines. It's faster.
It's fun.
Yeah, it's fun. It's fun. But by two engines, what do you mean? Anything in particular?
Can go faster.
Like redundancy?
Redundancy.
Yeah, got a lot of redundancy with two engines, two alternators, two vacuum pumps, all that good stuff. Okay? And it's fun to fly. In addition to that, as you're going further in your career, most professional jobs are going to require that you be able to fly an aircraft with more than one engine. Most commercial jobs are not going to be flying single engine aircraft. Now the multi-engine airplane flies just like the single engine airplane. It has the ailerons for roll. It's got the stabilator for pitch, the rudder for yaw. Everything works exactly the same way. You're going to find that it's very easy to fly. The difference comes when an engine fails. When an engine fails, we've got a few more things to do. Now in the Warrior, when the engine failed, what did you do?
Pitch for best fly.
Okay, so you pitch for a specific airspeed.
Found a place to land.
Look for a place to land in case the engine doesn't come back.
Attempt to restart.
Do a checklist to attempt to restart. And hopefully you'll get it restarted. Well, it's similar in the multi-engine airplane. In that, you're going to fly a specific airspeed. You've got a checklist to follow to see if you can get it restarted, and if not, address that engine failure. But you've got some control issues to consider as well. Now, in the single engine airplane, all we worried about was pitching down to go for the airspeed. We didn't worry about any yaw or any roll issues. In the multi-engine airplane, it's a little different. In the multi-engine airplane, again, as long as everything's working right, there's no problem at all. You've got equal thrust on each side, and you've got slipstream from the propellers blowing across the wings, giving us a little extra velocity or lift. But once an engine fails, for example, we'll fail that engine. Now what? We can see here, if we lose that thrust, it's going to have a tendency to yaw in the direction of the inoperative engine. Well, that's no big deal. We have a rudder. We can push on the rudder and keep it straight. In addition, we've got that propeller slipstream is minus on this engine, still operating on this engine, so which means we've got more lift on this wing than the other one, so we're going to have a roll issue. Again, no big deal. We use aileron to correct the roll. So when an engine fails, we're going to pitch for that airspeed. We're going to yaw for directional control, aileron for roll, do our checklist, come back around and land safely, correct? Maybe. Maybe. Let's take a look at that. Let's say we're in the Seminole and we've got these given conditions. We've got 22 degrees Celsius. We've got a pressure altitude of sea level, and we've got a weight of 3,600 pounds. 3,600 pounds. If you go to your information manual, page 5-24, go to the chart and put in these values. What rate of climb do we come up with? What's the rate of climb?
About 240 feet per minute.
240 feet per minute? Okay. So we're going to be able to climb at 240 feet per minute. Great. That's a whole lot better than going down at 700 feet per minute like you do in the Warrior. So we're going to be able to climb 240 feet per minute, come on back, land the aircraft safely. Again, we have to make sure we do everything right. If you look at this chart, at the top of the chart, it has associated conditions. Could someone read those associated conditions to me? Not too fast, because I'm going to write them down.
Wind flaps 0 degrees.
Okay, flaps 0.
Cow flaps, operating engine open.
Flaps open.
Inoperative engine closed. Landing gear up. Mixture full rich. Prop. Inoperative engine. Feathered. Power 2700 RPM. Full throttle. Airspeed 88 knots.
All right, and then you've got a note. What's that note say?
2 to 3 degrees bank towards operating engine.
Okay, so if we do all these things properly in a timely manner, we're going to be able to get 240 feet per minute on the climb to be able to return to the airport and land safely. That's a lot of stuff. That's a lot of stuff. If you go to the Seminole Training Manual, go to page A3. A3, which is in the emergency section. Would somebody please read to me what's in the red box there before the box that says, below the box that says warning?
In many combinations of aircraft weight.
Below the box that says warning. One that starts with mixture controls.
Mixture controls full forward. Prop controls full forward.
Go ahead.
Okay. Throttles full forward. Flaps full up. Landing gear selector check up. Inoperative engine identify and verify. Throttle from the inoperative engine close. Propeller inoperative engine feathered. Mixture inoperative engine idle cutoff. Establish bank 2 to 3 degrees into the operative engine. Climb speed 88 knots. Trim adjust to 2 to 3 degrees bank toward operative engine with approximately a half ball slip indicated on the turn and bank indicator. Cow flap and operative engine close.
Okay. So, as you were reading that list to me, I was able to check off every element from that associated conditions on that performance chart. The red box means what? Memory. So it's critical that we have those things memorized, because if we don't have them memorized and execute them, we will not fulfill all of the conditions necessary to get that performance from the aircraft when the engine fails. So that's very, very important. That's why that's in a red box, and the other stuff is not, because it's not part of the associated conditions. Okay? Now, as I look at this, for the most part, it makes sense. You know, we're reducing drag, getting the flaps up, the gear is up, prop feathered. Remember what the feathered prop is from your ground school? Increase angle of attack, blade stops, reduce drag. We've got full power, so we got maximum power. We've got mixture rich, full power. Airspeed 88 knots. Now that's a very important airspeed in a multi-engine airplane. It's so important that it's got a special mark on the airspeed indicator. On the airspeed indicator, you know, you've got your typical red line here at the VNE, but now we've got a blue line here. which is VYSE, best rate of climb, single engine. And that happens to be 88 knots. So whenever you're flying a light twin, no matter what the make is, as you look at the airspeed indicator, the blue radial is going to be the best rate of climb if you have an engine failure. So very, very important airspeed and published on the airspeed indicator. But I look at bank and 2 to 3 degrees towards the operating engine. I'm not so sure how that applies to performance or drag. So let's take a look at that. You know, normally with the single engine pilots, we think of coordinated flight with wings level ball in the center, correct? That's coordinated flight. So if we go to a multi-engine airplane here, as long as both engines are working, everything's great. That is indeed coordinated flight. Wings level, ball in the center. But when an engine fails, things happen. As we said before, we lose that thrust. We have the rudder that we have to apply because we're going to have the yaw, so we apply rudder to compensate for the yaw, to keep the aircraft straight. Now we use aileron to keep the wings level. What we have here is we have two different vectors. We've got a vector here moving the aircraft forward. We've got this lateral lift being produced by the rudder. If we have forces in two different directions, we're going to have a resultant force. So that resultant force, or in this case, direction of movement, will be like this. That's going to be the flight path. Even though we're holding heading, we're holding our wings level, we got the ball in the center, we're not flying in a straight direction. That means relative wind being parallel and opposite is like this. So that's going to have relative wind striking the side of the fuselage, creating drag, and going to decrease performance. We do not have an instrument in the aircraft that tells us that we're in this slip, but in our training aircraft we have a yaw string. And the yaw string will align itself with the relative wind. So in the windscreen we'll see that yaw string like this. That tells us we are slipping. We are not getting maximum performance. So the desire would be, well, let's take the relative wind from here and put it around to here. Well, how do you think we're going to do that? 2 to 3 degrees of bank. 2 to 3 degrees of bank. So let's take a look at that. So again, we'll have that engine failure. We've got the thrust from the operating engine. We still have that rudder applied to compensate for the yaw. So we've still got the lateral lift. But now we've got some bank. When we put bank into the aircraft, what happens to the total lift? You have a component of it that's going to be vertical and a component of it that's going to be horizontal. So we have a horizontal component of lift here. It's not a lot because the bank is little. But if we look at this, we see that if this force equals this force, it can cancel out so that now we're going to fly in a straight line. So if we fly in a straight line here, that means our relative wind is going to be coming more like this, and we reduce the drag, thereby improving performance by reducing the drag. Now, as far as the ball is concerned, that's being acted upon by gravity, so that's going to be approximately half out of center, approximately half out. You will have the yaw string, but in the Seminole, since it has that bar down the center, you won't see it. So if you're in zero side slip, you won't see the yaw strength. And that's a good thing for multi-engine flying. So it's important that you understand why we do these things and why that angle of bank is so important to eliminate the added drag of this slip, the side slip. Okay? So if you have an engine failure right after takeoff, follow the procedures. If you've computed a positive rate of climb performance, you should get it if you follow the procedures and fly the aircraft. Now, that's great. As I said, 240 feet per minute climb is better than going down at 700 feet per minute. But it doesn't seem like all that much, you know, 240 feet per minute. If we had both engines working, let's go to the page 5-23 in the manual and use the same conditions. What is the rate of climb with both engines working? Same conditions, 22 degrees, 3,600 pounds, sea level.
Maybe about 1,400.
About 1,400, okay. Wow, that sounds good. That's good. That's more like it, isn't it? Now, if we're climbing at 1,400 feet with both engines working, it would seem like, well, I just lost one engine. Why aren't I getting 700 feet per minute on the climb rate? So let's talk a little bit about that. Why is that? In the Seminole, understanding conditions of sea level, how many horsepower have we got per engine?
180.
180. So we've got two engines. That gives us 360 total horsepower. 360 total horsepower. Now, it takes a certain amount of that power just to carry this mass of airplane through the air in level flight. Now, I don't know exactly what it is to fly the airplane at 88 knots in level flight, but let's say, for example, it takes 150 horsepower just to carry it straight and level through at 88 knots. So what does that mean? If I subtract 150, that gives me an excess horsepower of 210. 210. So with that excess horsepower of 210, I can do one of two things. I can go faster, or I can climb at 88 knots at 1,400 feet per minute. Excess horsepower. Now, if I lose one engine, I'm down to 180 total horsepower. I still have to carry this airplane through the air at 88 knots. It may even be a little bit more than 150 because of the drag, but let's just use 150 so we keep our numbers straight. So I subtract the 150 now, and I end up with 30 excess horsepower. That's a huge reduction, isn't it? Much more than 50%. That's why now the excess horsepower is only going to give me 240 feet per minute climb at 88 knots. Again, better than going down. Better than going down. Now, something to think about too, what happens as your density altitude increases? What happens to available horsepower?
Decreases.
It decreases when we have a normally aspirated engine. So this excess horsepower becomes less. The higher we go, we have less and less excess horsepower. At some point, you will have no excess horsepower, which means you will not be able to climb. At some altitudes, you'll have a negative, and you'd have to descend down to your absolute ceiling. So this is an important figure to calculate. especially as you're flying in areas with higher terrain elevations. So to be aware of that, okay? So that's how you handle an engine failure shortly after takeoff correctly. Now let's say that you're a pilot, that you got your multi-engine rating quite some time ago and you haven't maintained your proficiency all that much with the single engine operations. And you're out there one day and you're taking off, you get full power, pitch up, you're climbing, and suddenly one of the engines become inoperative and you freeze. You freeze. Oh no. Well, you push the rudder to keep it straight, but you don't let the pitch come down. What's going to happen to the airspeed? It's going to decrease. Which means my rudder is going to become less effective. I got to push more rudder. If I stay with that high pitch, airspeed is going to decrease further. More rudder. At some point, I'm going to run out of rudder. And I will no longer be able to maintain directional control. That speed is VMC. And it's another very important airspeed that's written on our, that is indicated on our airspeed indicator with another red mark. Here on the lower speed, VMC. VMC. What is the VMC in the Seminole? What's the value? 56 knots. Very good. 56 knots. So, it's very, very important that the multi-engine pilot understands what VMC is and how to handle it. Number one, we want to avoid it. But in order to understand it, we have to understand, well, what is it? So let's take a look. I've printed out the definition in part 23 of the regulations. It says VMC is the calibrated airspeed at which, when the critical engine is suddenly made inoperative, it is possible to maintain control of the airplane with that engine still inoperative, and thereafter maintain straight flight at the same airspeed with an angle of bank not to exceed 5 degrees. So there's some conditions associated with it. One big thing to notice out of there is it says nothing about climbing, does it? It just says you'll be able to maintain straight flight. Might be straight to the crash site, but at least you'll maintain straight flight. But there are some conditions that apply to VMC. So VMC is not a constant airspeed, it's a dynamic airspeed. But there are certain conditions associated with it. Now, the Airplane Flying Handbook does not give us as good of information as it once did. So what is given as a reference now, and it's the best reference we have, it's pretty good. It's Flying Light Twins Safely. So if you haven't printed that pamphlet out, it's a good idea to print it out. So, VMC. It said the critical engine is inoperative. Critical engine is inoperative. Well, what's the critical engine? We can read in this Flying Light Twin Safely, it says a critical engine is the engine whose failure would most adversely affect the airplane's performance or handling qualities. Performance or handling qualities. It goes on to talk about P factor. That is the biggest factor involved in, well, what is the critical engine? So let's take a look at a multi-engine airplane. In a conventional twin-engine airplane, when viewed from the back, the propellers are turning in a clockwise direction. Both of them are turning clockwise as viewed from the back. So that's this way. As we pitch up, we have P factor comes into play. which means that the descending blade is going to create more thrust than the ascending blade. Correct? Everybody remembers the P factor? So in this case, the descending blade is here and here. So if we take a look at the total thrust across the disc of the propeller, we'll see that we'll have less thrust like this. Okay, more thrust on the descending blade. So if we look at the center of thrust on the right side of the blade, and we consider it to reference to the longitudinal axis, we can see the arm of that right propeller is greater than the arm of the left propeller. The longer the arm, the greater the effect. Therefore, the left engine, when it fails, would cause more of a control issue. So the left engine is the critical engine in the conventional twin. In the Seminole, Piper did us a favor by putting on two different engines. One has it turning clockwise, the other counterclockwise. So now, since the right engine is going to be turning counterclockwise, which will make the descending blade here, ascending here, we can see that the arms are the same. There is no critical engine in the Seminole. As far as the control issues are concerned, it's the same. No difference. So P factor is the primary element that's involved in the determination of the critical engine. It talks a little bit in this publication about spiraling slipstream and torque effect. Very, very brief, not real much explanation, just to say it exists, but it's not the primary issue to talk about with the P factor, with the critical engine. Okay, P factor. So that's one thing. We go on at page 3 in the publication. We've got some other factors that have to be considered, and they are, number one, power. Power on the operating engine. Maximum takeoff power, standard conditions at sea level. Standard conditions at sea level. Maximum takeoff power on the operating engine. The inoperative propeller. Is windmilling. Windmilling. That means it's not feathered. It's continuing to turn, and it creates extra drag. It's a windmilling prop. Now, if you happen to have an aircraft that has auto feather, then it would be feathered. Our Seminoles are not auto feathered. We have to actually do something about it. Auto feathers are nice, and they work. Another is center of gravity and weight most unfavorable. Most unfavorable. Now, center of gravity, most unfavorable. Every time we go flying, we figure our center of gravity. We see that it's within the envelope. So every airplane has a center of gravity envelope. So let's say this is our envelope. The two extremes are the forward limit and the aft limit, still within the envelope. But what we're talking about with this is the effectiveness of the rudder when an engine fails. So if we look at the arm from the forward limit, the arm from the aft limit, understanding that the longer the arm, the more effective, which would be the most unfavorable? The aft CG. Aft CG would be the most unfavorable. As far as most unfavorable weight, if we look at weight as a control issue, a lower weight would be less favorable because it would be easier to turn the aircraft. Now, the Seminole was certified back in the late 70s when the regulations were not the same as they are today. Back then, VMC was determined at maximum takeoff weight. So for the Seminole, VMC was determined at 3,800 pounds, maximum takeoff weight. So you can be aware of that. More unfavorable for control would be a lighter weight. Obviously, for performance, the heavier weight is more unfavorable. Next would be a configuration. Configuration. We've got the gear, well, let's not quite get configuration. We've got the gear up, gear retracted to determine VMC. Then we've got the flaps, cow flaps, trim, takeoff, configuration. Takeoff configuration. For airborne, the aircraft is going to be airborne and ground effect negligible. Ground effect negligible. And then we have bank. Max 5 degrees. Now let's not make that too big of a 0. 5 degrees towards the operating engine. So those are the factors. So in the Seminole, if the critical engine, there is no critical engine, it doesn't make any difference. We've got power maximum at sea level, prop windmilling. We've got the center of gravity full aft, maximum takeoff weight, gear up, flaps, cow flaps, trim set, airborne, 5 degrees of bank, VMC will be 56 knots. If any of these factors change, VMC will change. Example, power. Let's say we go to a higher altitude, so we have less power available. Will VMC be more than 56 or less than 56?
Higher altitude, you have it lower.
Okay, so you've got less thrust, less yaw, lower VMC, so it'll be less than 56. If the prop were to be feathered as opposed to windmilling, would it be less or more than 56?
Maybe less.
Again, less than 56. If center of gravity was forward,
Maybe
instead,
less.
it'd be less again. If the weight was lower than 3,800 pounds, VMC would be
If it's any lower, it would be greater.
higher than 56. Good. As far as the configuration is concerned, negligible. Bank. Bank is a big deal. Bank is a big deal. Bank affects VMC very significantly. And it's very, very important because bank is something that the pilot can control in flight at the time of the engine failure. It's also something that the pilot can control when the manufacturer is determining VMC. The steeper the bank, the lower the VMC. The shallower the bank, the higher the VMC. So let's take a look at that. Here we've got this other airplane. And we've got greater than or equal to 5 degrees on the bank. So we'll put a little bit more bank in there. And again, we'll fail that engine. We still have the thrust on the operating engine. We're going to use rudder to control yaw, so we're going to have lateral lift. With the greater bank, we have greater horizontal lift, which now it makes the balance out again, which moves the aircraft is going to be flying in this direction, which means the relative wind is going to be coming parallel and opposite in this direction. We'll see the yaw string like this. It makes the rudder more effective. So the more bank, the slower we can go. The manual says that VMC will change as much as 3 knots from 1 degree of bank. So if we go 6 degrees of bank, we could be down at 53 knots. If we went 7 degrees of bank, we could be down at 50 knots. So the manufacturer could manipulate VMC to be almost whatever they want if they didn't have a limit. So the FAA put that 5-degree limit on it. The limit is not on the pilot though. You know, if you're flying the airplane, you have an engine failure and you're losing directional control and you want to put in 10 degrees of bank in order to maintain directional control, you can do that. And it will work. But not very long. So if you do that, it needs to be at the same time you're pitching for the better airspeed, doing what you need to do, and then get back over here. Okay? But that 5 degrees is not a limit on the pilot flying the airplane. Also, with the greater bank, gravity is here. Now the ball is well out of center. Well out of center. So this also puts more weight acting laterally on the aircraft, which also has an impact on VMC. Okay? So we need to understand what VMC is, what is going to affect VMC, changing it, making it higher or lower. But the bottom line is, when you're flying, you don't want to be there. You want to be over here. If you have an engine failure, you want to be over here. If you end up over here, you want to get over here as quick as you can, right? Pitch for the airspeed, go through your checklist, do what you're supposed to do. But it's important that the pilots understand this. It's also required that we demonstrate VMC in flight. Now, the handouts give us a little graph, and on that, we have speed, and we got altitude. VMC with a normally aspirated engine, VMC decreases with altitude because of this. So we know what it is at sea level, and it decreases with altitude. We know that there is a point at which the aircraft will stall. If we continue to decrease the airspeed, increase the angle of attack, the aircraft will stall. We do not know what the single engine power on stall speed is. The manufacturer is not required to publish that speed, but we know there is one, and that one's fairly constant with altitude. So we can see VMC decreases. We don't know at exactly which rate. We know there is a stall speed. So if we encounter VMC at low altitudes, we will run out of rudder before we stall. If indeed we run out of rudder, the corrective action is to reduce the power on that operating engine to get directional control again, pitch for an increase in airspeed, and then smoothly apply power on that operating engine to accelerate back here to VYSC where you belong, right? That's the recovery. If we happen to be at an altitude that's higher, we will have an indication of a stall before we run out of rudder. Now, a stall with an engine failure is not a good thing to do. If you stall, you will lose direction control very, very quickly afterwards. So if there's any indication of a stall, the same recovery process is there. reduce the power, pitch down to increase the airspeed, smoothly increase back to full power as you're getting back up to BYSC and getting into the zero side slip. If, well not if, when we do the VMC demonstration in the Seminole, if we run out of rudder or we encounter the first indications of a stall, the demonstration is over. We're going to go through the recovery process, reduce the power, pitch, smooth full power on the operating engine. Okay, so wherever it is, it'll end right there. Now, the Piper manual mandates that we do VMC at or above 4,000 feet AGL. So at or above 4,000 feet AGL in the Seminole, we're always up here. We will get those indications of the stall first. You'll hear a horn, you might get a little bit of a buffet. It's time to recover. All right? So we'll have an engine with a prop windmilling and zero and powered idle. Center of gravity and weight's going to be whatever it happens to be. We'll have 5 degrees of bank. The yaw stream will be off into this direction. And we'll maintain that 5 degrees of bank until we get the first indication of the stall or we run out of rudder. Go through the recovery process. Okay? So, that's your introduction to an engine failure in a multi-engine aircraft. If we have an engine failure shortly after takeoff, this is what we need to do. Follow the checklist. Get all these things done. Acquire the predicted performance. Declare the emergency. Return for a safe landing. Do not try to get more out of the aircraft than it's able to get. You know, if you've computed that you're only going to get 240 feet per minute, don't try to get 500 feet per minute out of it. It won't help. You'll end up over here. You don't want to be over there. So it's important to know what to expect and don't ask anything more of the aircraft than what it says it can do. If you find yourself over in this region or even getting close to this region, change and get back over here. This is where you have the best opportunity of a successful single engine operation. Okay? Now for you guys, again, in training, your instructors, you're going to be failing engines, right? So you need to understand that you do not do engine failures at speeds below VSSE. What speed is that?
82 knots.
82 knots, okay. And you simulate the engine failure with the throttle only, below 4,000 feet AGL and above 500 feet AGL. Okay. Any questions or comments? Everybody understands, right? Okay. Very good.
I have something for you.
You got something for me. Go for it.
Should we mention to Tower that we're doing the single engine operation and the pattern? If we fail it on the climb out, or we just facilitate the best speed?
You should communicate with the tower because they have expectations. They may have other people taking off behind you. So if you say I'm doing a simulated single engine pattern, that gives them a heads up so they don't expect you to do something that you can't do.
They won't ask you for a left 360.
Well, they may, but at least they would know that you're doing a simulated engine failure. You know, if you're doing those simulated engine failures prior to 50% VMC on the runway, you should always request the option takeoff. If you request the option takeoff, they know what that means. That means you may be failing an engine prior to 50% VMC. Now, if the student does everything right, you can, okay, clean it all up, get ready to go, and take off. Once the option is complete, inform the tower that the option is complete so that they know they've got the full runway again. okay? So more communication is better than less communication. Is it mandatory in the pattern? Not necessarily, but it can, we have had some issues where when you're climbing out, they're expecting you to turn at a certain place and you're not doing it, and they begin to wonder what's going on. Any other questions? No other questions? Very good. I appreciate your attention. Make sure you print out that Flying Light Twin Safely, because the information is no longer in the airplane flying handbook. All the good stuff is out of that, and they reference you back to this. So, and make sure you get the one from 2008, not the one from 1978. I'm serious. They reference the 1978 number in the AC. So there's a newer one. 1978 is just when they were beginning to realize, oh, we need some bank on an engine failure. Okay.
Is the information from the old AFH, all of it's missing in there now, is all now in the Flying Light Twin Safely, or is it still missing some information as well?
It's not missing information, it's just not as well organized.
Okay.
It does not have a good definition of VMC. That's why I went to to print out the part 23 to give a good definition of it. But the rest of it is in there, and it's okay. It doesn't have the nice pictures that the old AFD had, so you'll want to have that to where you can maybe practice drawing things. But the information hasn't changed. VMC is still determined the same way it always was, well, as it was before. Any other questions?
So on our stage checks with the examiner, should we be referencing Flying Like Twins or the AFH, both?
They are both listed as reference material in the ACS.
Okay.
And to get the information that I just talked about here, the only place you're gonna get it is from that Flying Like Twin Safely.
Okay.
It's not in the Airplane Flying Handbook here. Anything else? Okay, thank you much.